Okay, so what I'm going to teach you today is this video is how to predict the strongest intermolecular force. So if I give you a molecule, you should be able to tell me which of those forces is the strongest. So the steps we're going to run through is first you're going to have to draw the Lewis dot structure. So this assumes that you know how to do that. Okay, then you're going to check for hydrogen bonding. This video also assumes you know how to do that. And then you are going to check the polarity of the molecule. And again, the video assumes all that. I'm going to go through it a little bit, but just quickly. So if you don't know how to do any of those three steps, you need to go back and watch the videos that apply to those three separate topics. Okay, what's going to happen here is that you are going to be looking for symmetry in a molecule, right? If it's a symmetrical molecule, it is going to be a nonpolar molecule, and that means the strongest intermolecular force, the thing that we're looking for, is London dispersion. If it's not a symmetrical molecule, it's going to be polar, and the strongest force will be dipole-dipole, unless it is a Lewis structure that has the hydrogen directly bonded to a nitrogen, oxygen, or fluorine, in which case that is dipole-dipole, but it's a crazy strong one that we separate into its own category called hydrogen bond or hydrogen bonding. What we're going to do is I'm going to use this flow chart that I created to help you through this, and we're going to work through some examples of this. And so let's get started. I have 4 examples for you. Okay, so when I look at these examples, the first one is the H2O. If you don't mind, I'm going to leave off the dots to save time. You end up with a structure that looks like this, and when you build that structure, the model is going to look like this one here. Okay, so let's go through our flow chart and see what we have going on. So is the molecule polar? Yes, this is not a symmetrical molecule. It is going to be a polar molecule. So my answer is yes. Does the molecule have a direct hydrogen-oxygen bond? And the answer to that is yes. When we look at our Lewis dot structure, the oxygen and hydrogens are directly bonded to one another. And so we end up with an answer of yes. So this molecule is going to be hydrogen bonder. Okay, so that is the strongest bond or intermolecular force rather inside of the structure. So we can say hydrogen bond. Okay, next I have CH3F. So when I do that structure, I end up with something like this. Okay, and when I build that, it looks like this. All right, so let's go back to our flow chart here. Let's cut that off, and let's see what we have going on. So go back to the flow chart. Is the molecule polar? Yes, this molecule is polar because it's not symmetrical. You have a green side here and a white side here, the fluorine and hydrogen. The fluorine is going to be pulling much harder for electrons than the hydrogen side, so this is considered a polar molecule. So again, we answer yes. Okay, does the molecule have its hydrogen directly bonded to the fluorine? Now this molecule does have hydrogen and fluorine in it, but notice they're not bonded to each other. They're both bonded to the carbon. So when we go to this question, does it have the H bonded directly to fluorine? The answer is no. So this is going to be a dipole-dipole. That is the strongest intermolecular force in this molecule. So let's write that up on there. So this is a dipole-dipole. Okay, next one is the sulfur trioxide. When you do this one, if you finish out the dots, you end up with a double bond in there. This is a resonance structure. Okay, so we end up building a model that looks like this. So let's go through our flow chart again. So is the molecule polar? The answer to that question is no, it's not polar. This has every single side of this molecule pulling equally for electrons, very symmetrical molecule as far as the atoms are concerned. So is the molecule polar? No. So it has to be a London dispersion. So we'll write that on there. Okay, the last one is the CH2S. So when you build this one and put in all the dots, you end up with a double bond to the sulfur. So the molecule looks like this. Okay, so let's go back again to our flow chart. Is the molecule polar? Yes, this molecule is polar. This side of the molecule is different than the other side. It's pulling differently for electrons. So we would say yes. Okay, does it have a hydrogen bonded to a nitrogen, oxygen, or fluorine? The answer is no. There's not even a nitrogen, oxygen, or fluorine in this structure. So if the answer is no, this again becomes a dipole-dipole. And so that is the strongest intermolecular force in that structure. Okay, so this is a set of 4 examples then of how to figure out which is the strongest intermolecular force in a simple molecule. If you need to do the boiling points, I will try to make another video for that to figure out, relatively speaking, how high the boiling points are. Hopefully you figured out how to do this. Thanks.